So let's go ahead and see what that looks like for the chicks data. Oops, gotta make that the active window. So first, I'm just going to use a little dplyr here to take the chicks data, group it by treatment, and compute the mean. And that gives me 100. This is the mean for grams at day 25, which is our key outcome in this experiment. So that was 1,100 grams for the involuntary bucket and 972 grams for the voluntary walk-on. So it turned out that the ones that were being trained to walk onto the scale actually didn't gain as much weight as the ones in the involuntary bucket group. And in fact, if we take the difference in means, we get a number 128.13 grams, but it's negative, meaning that the ones that were doing the voluntary walk-on gained less, which wasn't what the scientists expected, right? Their hypothesis was the other way around. I'll give you a preview. The data set's very small, right? So, sorry, I didn't mean to split the slides. The data sets, you'll see in a minute that the data set's very small, and so it's hard to interpret this outcome. But at its face, we're seeing that those ones that were scooped up in the bucket gained more weight by day 25. Why are we doing this with an experiment? Why do we do the randomization of assigning the chicks randomly to one group or the other? The reason we do that is the difference in means is an unbiased estimate of the average treatment effect. So you have to sort of think about what unbiased means. So unbiased means that if we did this experiment hypothetically over and over and over again, the average of all the tau hats we get should be the true average treatment effect. Hopefully that makes sense. So, so in theory, we could do the same experiment over 1,000,000 times, and each time we would get a different tau hat that would bounce around the true average treatment effect. But then if we took the average of all of those, that should be the true average treatment effect. There's one assumption that you have to make for that to be true, which is that the potential outcomes for one subject do not affect the other subjects. And this assumption has a fancy name. It's called the stable unit treatment value assumption. So that assumption means those potential outcomes are what they are, and what I do with other subjects does not affect the potential outcomes for another subject. In marketing experiments, we sometimes have violations of SUTVA. If, for instance, the treatment is to give someone a coupon and they pass the coupon or the coupon code along to other people, then you've violated SUTVA because the fact that that person got the coupon affected what was going to happen for the other person. Another way to think about this that people talk about is that the randomization eliminates the possibility of confounders. So confounders would be things that go together with the treatment or go together with the control. And when you analyze confounded data, you can never be sure if it's the treatment or the confounder that's really causing the effect. But in a randomized experiment, we kind of break the potential of a confounder because the randomization couldn't possibly have been associated with anything else because it was random. All right. So I had one other little aside that I wanted to drop on you. The average treatment effect is actually the average of the population that is in the experiment. So ideally, if your experiment can't be the full population, it should be a random sample from whatever population you're trying to study. So in engineering experiments, that's trivial. Like, say, if I want to see how two different manufacturing processes perform, I can easily sample the parts that I want to include in that experiment off the line at random, no problem. It's also fairly doable in marketing experiments where we can just toss a coin to decide whether each visitor to our website, say, is in the experiment or not in the experiment. And so that makes it fairly easy for us to take a random sample of the visitors to our website, which is usually the population that we're interested in. But in other populations, it's unethical. Like it would be unethical to randomly sample from Americans and force them to be in a vaccine trial. And so we typically don't do that. But then you always have to keep in mind that when you compute an average treatment effect from an experiment where you didn't sample at random, then the population that you're studying may actually be slightly different than the population that you're interested in. But it's good to know that in the ideal experiment, there's kind of two types of randomization. There's random sampling to select subjects and then random assignment to treatment. That would really be the ideal if you can get it, if it's not unethical. All right. So let's get back to analyzing the chick data. So a typical way to analyze this kind of experiment is with a t-test. So the R syntax for a t-test is t-test, and then I can use our formula notation here. So I just say the variable name is a function of the treatment, and then I tell it that the data is in this data frame called chicks, and it gives me this sort of obtuse output. Maybe some of you have used this before. So the t statistic is 1.3 and the p-value is 0.2, and that kind of tells you it's a measure of how much data do we have, and are we pretty sure that we have the right ATE? Because if we have less data, then that the estimate of the ATE is going to bounce around a lot more. And so what we're trying to do here is give ourselves a sense of how much could the true ATE be bouncing around. And the thing I like to look at is this 95% confidence interval, which is minus 71 to plus 328. So that means we're not very sure about the difference between these two weighing treatments. So the experiment is sort of somewhat inconclusive here. Some people like to look for a p-value of 0.05, which would say that we have enough data to say whether the difference is positive or negative. We have quite enough, we feel like we have enough data to say that either one treatment is better or the other treatment is better. But here where it's a bit equivocal, it's sort of leaning towards the idea that the bucket treatment produces chicks of higher weight. But there's some possibility that it's the other way around. All right. I'm sorry, I got distracted by the chat. No, I like Cook and someone asked a question in the chat about Cook and Campbell, which is a classic book on the design of experiments. And yeah, I think that's a great book. All right. Let me get to another way that we can analyze an experiment, which is with a regression. So we can use LM, which is the function for running regressions in R, and we can say that the grams at day 25 is a function of the treatment using the same R formula notation, and telling R that the data is in the chicks data frame. And that gives us output that looks like standard regression output, where the kind of important number is here, this treatment voluntary walk-on, and that's where we see that minus 128, which we saw before, that the difference between these two treatments on average is 128 grams in the data. And it tells you about the uncertainty in a slightly different way. So the p-value here is 0.19 on this coefficient on the treatment effect, which is actually very close to the 0.2 p-value that we saw in the t-test, telling us this is not statistically significant. This standard error is actually telling you how much we think that the estimate might bounce around that minus 128 value. So it's basically telling us the same thing in a slightly different format. It tends to be different disciplines prefer one or the other of these. Like my mother, who is an animal behaviorist, tends to do t-tests, whereas economists tend to use regression for these kinds of experiments. All right. Oh, and there's another function I wanted to tell you about. I don't know, this is not that common of a function. So M1 is the name of my regression model. So with regression, I forgot to explain this. You run the model and then you assign the model object to something, and then you can do other things with that model object. And that's a syntax we're going to see again. If I do M1, I do a summary of M1, I get this text output, which is the traditional regression output. But if I do confint of M1, it tells me the range of the likely range of the coefficients in the regression. So these two numbers here are telling me my regression at, confidence interval for the treatment effect, which is minus 324 roughly to 68. And we can compare that to the one we got from the t-test. So it's pretty similar. The t-test is slightly wider, it looks like. But it's very close to the same thing, and it's telling you your estimate of the treatment effect is slightly different. Can you talk about objects of class formula? That is a very good question. If you have grown up in the tidyverse, you probably haven't seen too many of these formulas. So a formula is, as you probably figured out, since you know that it's a class, it's a class in R that we use to describe traditionally regression models. So I'm saying I have an outcome that's always on the left-hand side of the little tittle. So that's a tilde. It's above the tab key on my MacBook. So on the left-hand side of that tilde, I put whatever my outcome variable is, or my Y variable in regression analysis. And on the right-hand side, I put all of my predictors. And I can do different things with that. So I can add multiple predictors. Here I just have one predictor treatment, but I can use multiple predictors. And if you go to some of the older packages, this form of notation is sort of ubiquitous across older packages. So lots of the base R packages use this formula syntax to describe models. And you can see I'm kind of doing the same thing with these two functions, and they use the same formula object. So the t-test grams day 25 tilde treatment to say, I want to predict grams day 25 as a function of the treatment. And here I want to predict grams day 25 as a function of the treatment. And it sort of conceptually allows you to separate out the model that you want to fit from the data. Now, when Julia comes, you should all go to Julia's talk. I will probably go to Julia's talk because the tidyverse has its own way of thinking about models that doesn't use this older form of notation. One thing you should know, let me just switch to R quickly. So let's see, I have, well, can you guys see that at the bottom of my screen? I should make it bigger. There we go. So at the console, if I do plot of y tilde x, whoops, that's because x isn't. It plots y as a function of x. So it puts y on the y-axis and x on the x-axis. So a lot of people don't know that because they grow up with ggplot, but the old-fashioned base R plot function also uses these formulas and can interpret them in kind of the way you would expect. I want to predict y as a function of x. And if I want to do that in a plot, I want a picture with x on the x-axis and y on the y-axis. But that's a good question. All right, let's go back to the slides if I can find them. All right. So we looked at the confidence interval. All right. So that was just the basics. That was the preliminaries of what is an experiment and how do we usually analyze it. So the big takeaways are randomized experiments allow us to estimate the average treatment effect by a simple difference in means calculation. And we can characterize our uncertainty in that estimate or how confident we are using a t-test or a simple regression of the outcome on the experiment. No, Helen, you don't have to say sorry. Not at all. And thanks everyone else for filling in the chat Helen's questions. That's great. All right, I'm not seeing everything in the chat, so if I miss something that's important, I guess Alice or Jessica or someone will interrupt me.
Yeah, actually, we're tracking it. No worries.
Okay. Now's a good time to pause. Is there anything else?
I actually think that's it.
Okay, yeah. Good. I see, Alice, that Tidy Models does use formulas. I haven't dug into Tiny Models yet myself. I started using R in 2005-ish. So I have a lot of old-fashioned habits. All right. Next, we're going to talk about treatment modifiers, which have a lot of names. They have other names like pre-randomization covariates or baseline variables or lots of other names. I'll try to give you those names as we go through it. So the idea of a treatment modifier is this. Treatment effects might actually be different for different groups of subjects. So for instance, if I take this chicks data and I group it by color and treatment, so that now I have 4 groups. I have the brown ones and their 2 levels of treatment, and I have the white ones and their 2 levels of treatment. If you look at that, it looks like for the white chicks, there actually was no difference between the 2 treatments. They're actually, like in the data, the averages are the same, 855 grams. But for the brown chicks, first of all, it seems like brown chicks are bigger. And they, you'd have to ask a biologist why they're bigger. I'm not really sure. And the involuntary bucket treatment for the brown chicks gained a lot more weight than the voluntary walk-on chicks. So that is what I mean by a treatment modifier. It seems like somehow the color is affecting the treatment. We know the data is kind of thin here, but if we believe this data, it's suggesting to us that there is no effect of this treatment on the white chicks, which is sort of surprising, but that's the idea of a treatment modifier. And we can think of other, lots of plausible reasons why a treatment might only work on one subgroup of people. So for instance, if you were, say you were Comcast and you were sending coupons to people that they could get a discount on the first 3 months if they sign up for cable service in addition to their internet. They sign up for cable TV. Well, if people already have cable TV, then maybe that treatment doesn't do anything to them if they already have cable TV with Comcast. But if they don't have cable TV with Comcast, then there is a treatment effect. So that's a plausible mechanism for differences between subgroups. We can also think of biological examples where, if a baseline variable might be how many vaccines for that disease have you received prior, and we would expect the treatment effects to be smaller for people who've never received a dose of that vaccine before and higher for people who have never received that vaccine before. So that's the idea of a treatment modifier. Here I go ahead and compute the difference in mean. So I'm just taking the difference between the voluntary walk-on and the involuntary bucket for the brown chicks, and that's -170. And for the white chicks, it's 0. That is not how we typically do subgroup analysis. It's most often done with regression. So we can incorporate those modifiers in the regression analysis using what's called an interaction. So let's look at this formula a little bit closer. So I'm going to run a regression. M2 is going to be a linear model with this formula here. I don't know if you guys can see it better or worse when I highlight it. Let me know in the chat. So Graham's day 25 is a function of the color and the treatment. And this thing where I say treatment colon color, and that's an interaction term. And the formula literally means multiply the treatment variable by the color variable, like multiply those two things together. And add that to your linear regression and have a term. So it basically, this function is saying that the Graham's day 25 follows an equation that has an intercept. There's always an intercept, so we don't have to say it, plus a effect for the color, an effect for the treatment, and then an effect for the color times the treatment. And I'll show you what that does in a second here. If we look at the regressions, you can see the important parts of the regression. It's cut off on the bottom of the screen. So the intercept is 1,175.17 grams. The color effect is minus 320. And that's saying the white ones, when the color is white, so it says color W. When the color is white, then the chick's weight at day 25 is 320 grams less. And then the treatment voluntary walk-on is 170, and that's for the brown chicks. And now the regression is cut off. Bummer. Well, yeah. There's one more line here that you can't see. I'm sorry about that. If you're running the R Markdown file, you can see it at home. And that is that interaction effect. And what that number is minus 170.13, sorry, plus 170.13. And what that means is, so the intercept is the baseline, which would be, in this case, brown, and the bucket, the control group, brown in the bucket. Then the color W effect is minus 320. So it's just on average, the white ones are not gaining as much. The treatment effect for the brown ones is 170.13. The interaction term, negative 170.13. The interaction term is positive 70.13. And that means for the white ones, you have to add those two numbers together and get 0. And so the treatment effect is 0 for the white ones. So that's how we kind of the old-fashioned way of using regression analysis to figure out what the treatment modifier is and how much that treatment modification is. Let me give you some vocabulary for that. Actually, let me pause. Questions about that? I feel like that was a little hazy. I see Jessica is asking, does the color have anything to do with the chick breed? No, it doesn't. They're all the same species of rheas. And I was more wondering if there's any questions about interactions, or is that stuff you've seen before? All right, so what we're doing here, if you look at this equation, we're trying to figure out this thing that's called a conditional average treatment effect. And by what I mean by conditional is for the subgroup. So for the brown ones versus for the white ones. And so I can say, oh, the treatment effect, the expected treatment effect for a certain value of X, that's what I want to know. Or another way to write that is the difference between Y1 and Y0 for a particular value of X. So this kind of analysis is sometimes it goes by many, many names. Sometimes it's called effect modification. Sometimes it's called stratified analysis, because people use the word strata to describe these groups that are defined by X. The economists tend to call it heterogeneous treatment effects, but we're trying to find these conditional effects, like the expected treatment effect given a particular value of X. All right, I put in some asides about our formulas for fun with our formulas. So color plus treatment plus the interaction between treatment and color. That's what I wrote before, but you can write it another way. You can write it as color times treatment. Cool, huh? So that actually means the same thing as this other formula here. Another trick is that if you don't want to have an interaction, you can do 0 plus. And that means I don't want an interaction. And what that does in this case is it gives us a number for color brown, another number for color W. So, oh, and I have the wrong Y here. That's why the numbers changed. Can Jessica or Alice, can you write a note that there is a typo on slide 23 and 24?
Yeah, totally.
I will fix that after the talk. I used the % gain instead of the gain, the day grams day 25 variable. But I was just trying to tell you about these other tricks with formulas. You should Google around for tricks with our formulas because there's like lots of convenient things you can do. All right. The last thing is I wanted to give you a word of caution. So the variables, before you go too crazy with these subgroups, if the variables that you define the subgroups by are something that could be affected by the treatment, so that the treatment could actually change which subgroup you're in, then the estimates of the subgroup treatment effects are no longer these valid, unbiased conditional average treatment effects. So you can't use things that happened after the treatment was assigned because those are all plausibly affected by the treatment. So for instance, we can't use the weight at day 10, which is in our data set. We should not use that as a subgroup definer because the weight at day 10 could have been affected by the treatment, which began at day 0. And so we shouldn't use that variable. So we typically use variables that were collected before the randomization. So another name for this modifier variable is pre-randomization covariates. That's what the economists call it, to emphasize that it had to be before the treatment started. The epidemiologists sometimes use the word baseline variable to mean it was something that we measured for the subject prior to them being assigned to a treatment. It's actually okay if it's something that you measured after the treatment was assigned, after the randomization, but it's something that could not have been changed, that could not have been affected by the treatment. Something like the person's natural hair color, like the chick can't, or the chick's colors. You know, even if we collected that color data on day 25, it couldn't have been changed by the treatment. Unless something really crazy is going on with the behavior modification. All right. Last thing you need to know about modifiers before we're ready to get to the causal forests. There can be multiple modifiers. So you can have as many modifiers as you want. So we have color and sex. I can put both of them in. The way I would do that is with this color and treatment, and the typo continued to page 26. Can someone get that?
Yeah, I'll take a note for you, don't worry.
Thank you, Alice. And so we can run a regression with this formula, and now we're dividing into lots of subgroups. So that we have the brown ones that are female, and the brown ones that are male, and the white ones that are female, and the white ones that are male. So now we have 4 subgroups, and you can keep going with this game as much as you want to find all those like you know, potentially interesting subgroups that have different treatment effects than the average treatment effect. And that's where the causal forests come in. So if we have variables that are unaffected by the treatment, we can use them to create these subgroups and estimate the conditional average treatment effects for each subgroup. The problem with this is it kind of rapidly gets out of control if you're going to do it with this regression that I showed you. So for the chicks experiment, we have 5 potential modifiers. And we don't know which ones are important. Like me analyzing it, I don't have any strong theory about why the color would affect the weight gain or any of that. I just have these 5 variables. And if you go to sort of large marketing experiments, you might have hundreds of potential modifiers, like literally hundreds, because say, for instance, when Facebook does an experiment, they have like data on everything they know about you from all your last 5 years of interactions with Facebook. And so there's potentially a lot of modifiers, and you don't necessarily have strong theory to tell you which ones you should be looking at. A second issue that we run into is in the chicks data, we have 2 continuous modifiers. So we have the hatch date, which, you know, is along a whole range of days. And we have the grams at day 0. That's a potential modifier, right? Because yes, it happens after they are lured onto the scale, but we shouldn't have affected their weight by that first treatment. So arguably that's a good potential modifier, like how big was the chick when it came out of the shell? And that one is in grams with fractions. So, you know, it's a continuous variable. And if we put those continuous variables into the linear regression, we're going to assume a linear relationship between the treatment effect and the modifier. And we don't necessarily know, you know, maybe the grams day 0 has like a curvilinear, like a upside down U-shaped relationship with the treatment effect. And so the best thing we could do is maybe like cut the grams day 0 variable into buckets and stick those into the regression, stick dummy variables for that in the regression, but it just gets really clunky really fast. The other thing is we've got a few NAs for the sex, and LM actually throws out those incomplete cases. It can't do anything about those. It doesn't know what to do with those LMs, so it throws away the whole record. And if you've got like a lot of potential modifiers and a lot of NAs, like only analyzing the complete cases can kind of limit your power to figure out what is actually going on. So, so it's a good idea to like find a way that we could actually keep those records with the NAs. And that's where causal forests come in. So causal forests are a flexible way to identify important modifiers from a large set of potential modifiers and relate them to the treatment effects so that we can find these subgroups that have big treatment effects, small treatment effects, whatever. We can find those heterogeneous treatment effects and potentially use them. So this is also a good place to stop for questions.
One question in the chat that wasn't answered from Jessica: how to estimate the treatment effect in brown chick from the regression model.
So the brown, yes. Yeah, I didn't explain that very well. Thanks for backing me up, Jessica. So let me go back to the first. Oh, you mean the one, yeah. So this one, that has the right outcome variable, grams day 25, and we have the color and the treatment and the color treatment interaction effect. Yeah, let me do this. So give me just a second. I want to answer it correctly for you. So we are here in the markdown file. I'm not sure what I was doing in here last. So we did the regression. Here we go. We could just look at this. Can you see that? Get a little bigger.
Yep.
Yep, there we go. So there's the full regression output. So what happened here is that R automatically turned my color into a variable that is 0 when it's brown and 1 if it's white. And it turned treatment into a variable that is 0 when it is involuntary and the bucket, and 1 when it's voluntary walk-on. And this formula means, like, what would I multiply that color 0, 1 variable by to get the grams day 25? So that's the linear regression part. So it's like an equation for a line. But you have to know that that color variable is going to be automatically transformed from a factor. It begins as a factor. That's what it is in the, so if I do an STR of chicks, oops. Oh, it's not loaded. Hold on, just has to catch up with us. So if I do STR of chicks, that's the same as the old-fashioned way of doing glimpse. You can see that the color variable is a factor with 2 levels, brown and white. And so that's when you start with a factor, R knows how to convert that into what's called an effect code. So it takes that color factor and transforms it to a variable that is 0 if it's brown and 1 if it's white. And that's why I knew that this intercept was the baseline for brown, because color is the 1 and 0 is the brown. So this number is our base amount of weight for brown chicks that got the bucket treatment. And then if they're white, I subtract 320. If they had the voluntary walk-on treatment, I subtract an additional minus 170. But then if they're white and they got the voluntary walk-on, I add back 170. And so this minus 170 plus 170 gives us the effect for the white ones, which is 0, which actually we saw was 0. If I scroll up here, you know, we saw up here when I computed it by hand, just taking the difference in the means, I got a 0. So these regressions are sometimes very tricky to interpret. I usually go back to the, just this kind of basic calculations to make sure that I'm interpreting it correctly, because sometimes it can be tricky to think through, well, what is this variable, this color variable, how has it been transformed, and then how do I multiply it by these other numbers? It's just like a lot to think through. So sometimes even I double check myself by going back and just doing the calculation manually. You might be wondering, why are we doing this regression at all? And it's because it gives us a convenient statistical uncertainty estimate. So we have this standard error, which is a measure of how sure are we what this number right here is. So we think the treatment effect for brown is minus 170, but it has a standard error of 104, which means the confidence interval, if I go down here, is going to be very wide. So for the brown ones, the treatment effect is between minus 384 and 43. And for the white ones, I have to do even more arithmetic to figure out what the treatment effect is. But we do the regression just as a convenient way to get that statistical uncertainty analysis. That's the only thing that it adds over doing the basic calculation. What else do we have? Oh, that's a good question, Amanda. So when randomly assigning treatments to subjects, is it valid to assign treatments in a way that you ensure equal group sizes for each subgroup, e.g. randomly assigning half the brown chicks to walk on? Yes, that is absolutely the best way to do it, is to, if you have an even number, to then divide it by 2 and draw half of them from a hat. And that would be a good way to come up with the right number. Sometimes in experiments, we run into problems where the subjects are coming in a stream. This happens in clinical trials, like not everybody arrives on the same day so you can also just toss a coin when that subject arrives and assign them, but that won't give you exactly the same number in the treatment and the control. That's a good question. All right. I see way back there, there's a question, what is the difference between forest causal and normal linear regression based causal inference? I am about to get to that. So we're finally going to get to the causal forest part of the things. All right, let's go back to the slides. All right. So this slide with the challenges with using linear regression for subgroup analysis was kind of my motivation for why we want to look at causal forests. So causal forests are going to give us a way to identify important modifiers, even when we have a whole bunch of them that we need to sift through. And it will give us a way to relate those modifiers to treatment effects. So that we can say, this is the relationship between the treatment effect and this modifier. This is what the treatment effect is for this particular subgroup. And I told you, so we're at slide 30. And I have to do a few things. I told you we wouldn't get to the causal forest till slide 37. And so I have to do a few more preliminaries I apologize for. Is now a good time for a break?
Yeah, we can go ahead and take, it's 5 minutes good? 5-minute break?
Yeah, I think so.
Okay, I'll go
Jessica,
ahead
when do you
and,
want me to finish by? You have some stuff to do at the end, right?
I think it'll take me less than 5 minutes to announce raffle winners.
I
10
think we
minutes.
will be done well before then, because
Okay.
I have about 20 slides to go. I think we're in good shape for time. So let's take a break.
Awesome. Okay, I'll start a timer for 5 minutes starting now.
Great.
Then take it away.
All right, so we'll get to the causal forests pretty soon. The package I'm going to use for causal forests is this package called GRF. So the causal forest method, if we start at the homepage for the package, it's just so much. A package for forest-based statistical estimation and inference. You might not even know what it does, but I should acknowledge, so this paper, Susan Athey and Stefan Wagner, Estimating Treatment Effects with Causal Forests, is a really nice introduction to the idea in general. This second paper is a very technical paper that gets into the details of why causal forests work. So I thought this was kind of a good opportunity to tell you a little bit about how I approach a new package. I found out about this package at a conference. And the first thing I went for was a tutorial. You can see the tutorial is like pretty technical. They're trying to explain why it works, keep going. And then we get to an example. And so I based a lot of what I'm going to show you on sort of following this example and applying it to my chick data. All right, so the first thing I learned in that process was that the package, the GRF package, doesn't play nicely with those R factors. So you saw that I have R data stored. The chicks data has like breeding group is stored as a factor. And that's nice because it plays very nice with the LM package and a bunch of other base R packages. But the GRF package doesn't follow that convention. So all the variables have to be numeric. So I'm going to create 5 potential modifiers that are numeric. So the first one is breeder. And so I'm going to say if the chick's breeding group is breeder, if that's true, you get true, and then you multiply by 1, and that gives you a number. So that'll give you 1 if it's breeder and 0 if it's non. The hatch date, I'm just going to use the as numeric function to convert that date to a number using whatever, R has its standards for storing dates as numbers. So just convert that to a number. The grams is already a number, so I can leave it how it is. So I'm just storing it in grams day 0. The female variable, I'm doing that same trick where I say if the chick sex is female, then that'll be a 1. If chick sex is male, then this will be false. And when you multiply false by 1, you get 0 for male. And same thing for brown. So we've got our variables, they're now numeric. All right, I have to give you some preliminaries to explain exactly how the causal forest works. So step 1 is classification and regression tree. So this idea has been around for a long time, like maybe the 70s. It's called CART, or classification and regression tree. And it's an alternative to the linear model for regression. So what you do is you take all of your subjects, and then you come up with these splitting rules where you say, if the grams day 0 is less than 1 value, you go to the left. And if it's bigger than that 444.53, you go to the right. And if you go to the right, you get to this purple thing, we call that a node. And that node, the prediction is 12, 15, 65. So if you are bigger than 444.53 grams on the day you're hatched, then I'm going to predict that your grams day 25 will be 1,215.65. So there's no line, not all the things that you might be used to from regression. It's just these simple rules. So if you're less than 444 and you are male, which would put us female less than 0, so that's male, I'm going to predict 1,126. And if you're female and you're small, I'm going to predict 1,095. So I only can ever predict 3 different numbers based on this CART tree. So I predict those node numbers depending on where you fall into the classification tree. The way these things are estimated is much more of a machine learning style thing, where you actually consider a splitting rule. Like you consider a whole bunch of splitting rules and figure out which one you think is best in terms of separating out groups that are different in weight at day 25. And you do that split, and then you take that node. And of course, this node has size 1, so you can't split it anymore because there's only 1 observation in that node. But like this node that's size 4, we could consider splitting that again. And you have some rule that the split has to be good enough to actually do. Otherwise, I stop and I leave that as a leaf with the prediction. And the prediction is actually the mean of the subjects that are in that part of the tree. Does that make sense? Any questions about CART? So this is a tree that is predicting the weight at day 25 from all the other potential modifiers. That's not a causal forest yet. That's just a classification and regression tree. Next, we have to think about random forests. So a random forest is a bunch of CART trees, forest trees, so kind of go together. So what you do to build a random forest is you take a sample of the data and you build the best tree for that sample. And then you take another sample from the data and you build the best tree for that. For each tree, you have a prediction for each unit. So for each observation in your data, you can go down a tree and get a prediction for it. But now you have a forest, so you can get a prediction for each of the trees in the forest. And then you average those together, and that's your prediction for the unit. So that's what a random forest is. And it's an example of an ensemble technique that's called bagging. So bagging is when I build multiple models and then I average them together, and that gives me my prediction. So that's what a random forest is. And we can fit a random forest using the GRF package. So in fact, GRF stands for generalized random forests. So it wants the inputs in terms of a Y variable. So that's your outcome. So that's my chicks grams day 25, a W variable, which is the treatment variable. Oh, we don't need W, sorry, the W shouldn't be here. And then an X, so you can just ignore that W line. And the X variable is gonna be, I'm just gonna make a data frame with those 5 predictor variables. And then I stick the X and the Y into this regression forest function. I say I want a forest with 100 trees. And this process is random because we have to sample the data. So we sample the data, build a tree, sample the data, build a tree. And so it's good to give it a random number seed. So I gave it today's date, just so that when I run it again, I'll get the same answer because the random forest is random. So, okay, so I run that code. And I assign the model object to RF for random forest. That's just my variable name, but this is the function that you need to call, regression forest. So then I can actually look at the trees in the forest. We can see the trees for the forest or something, some insert silly joke here. So if I do get tree random forest 1, that's saying, give me the first tree. And then there's a handy dandy plot function that GRF provides that will plot the tree. So this is what the first tree looks like. We take the breeder variable, and if breeder is less, this is hard to read, but if breeder is less than 0, meaning breeder, it's not a breeder, you go down here and you predict 961. If breeder is greater than 0, meaning it is a breeder, then there's 4 subjects like that and 802.87. The reason we have our original data set had 33 subjects. The reason it only has 8 here is that random sampling. So it's randomly sampling and building a tree from 8 observations. And then it does that again, and it gets a different tree. So that's tree number 4. So I got the tree from tree number 4. You get the idea. There's 100 of these different trees. And then if we want to use that random forest, we would, and we want to make a prediction for any observation, we'd go down the tree for that observation. For each tree, we'd get 100 different predictions, and then we average them together. And that is our prediction for that new observation. So that's a random forest, still not a causal forest. This is a random forest that was built to predict it predicts Y, which is the grams at day 25, as a function of X, which is our modifier variables, but we still haven't brought the treatment in. We kind of that's been sitting off on the side. Oh, I forgot about this slide. Here's a picture of what the predictions look like. So I take this RF predictions, we'll pull the predictions from the random forest for the observations in the original data set. And I'm plotting the predictions against the hash state. And you can see it doesn't follow a line like a regression would. It has all these sort of different values. It could actually, like, you could have shapes that were more U-shaped, or it could go flat and then up at a certain point. It could take on lots of forms. This happens to be what it looks like for the this random forest, which predicts weight as a function of the modifiers, but we still no treatment yet. So now we are finally ready. Really, this time I'm really going to get to the causal forests. So I thought I'd show you the documentation. So this is a screenshot of the R documentation for the causal forest. So it says it trains a causal forest that can be used to estimate conditional average treatment effects tau x. So that's a funny way of writing it, but then they are clear down here. When the treatment assignment W is binary, so that's the treatment W, and unconfounded, we have tau of x, which is their individual level treatment effect, is the expected difference between Y1 and Y2. So those are the outcome under treatment, the outcome under control, conditional on x equals x. So you've seen all that notation. If you see that documentation, at first it's like, whoa, what are they even talking about? But because we did all that prep work, you guys know what we're talking about. which is we're trying to estimate these individual level treatment effect as a function of the potential modifiers. And the forest is going to allow us to, so what we're going to do is we're going to build a random forest, but instead of predicting the outcome, we're going to predict the treatment effect. That's the twist. That's like kind of the whole idea. So we're going to take a random forest, and instead of building a random forest to predict the outcome, we're going to build a random forest to predict the treatment effect. And that's what's going to allow us to sort through all those potential modifiers and figure out, like, we'll have these trees that tell us if this, this, and this, then the treatment effect is bigger. And if this, this, and this, then the treatment effect is smaller. So let's do that. So it turns out, after all of that explanation, it's super easy to do with this package. So we're going to call this function called causal forest. And so the function is causal forest. We have to give it X, Y, and now W. W is important. You also need to tell it this W hat, which is the probability in the experiment of being treated, which was 50-50 in this experiment. So each chick we tossed a coin, 50-50 is the chance that any given chick was treated or in the control. So just to remember, X are our potential modifiers. They're in a data frame. There's 5 of those. Y is just a vector, and it's our outcome, which is grams day 25. And W is that treatment indicator for whether they got the bucket or the walk-on. And I have a random number seed here, which is my anniversary. So now I've run that code. Now in the CF object, I have my causal forest. So what can I do with it? Well, the whole point of this was to estimate those conditional average treatment effects. So one of the things that the package gives me right off the bat is this CF object has a bunch of predictions, which are the predictions from the causal forest of the treatment effects. So these are not the weights, these are the treatment effects. Remember, our average treatment effect was something like -128. And so here I just stacked together those predictions in a data frame along with the X's. So you can see this one that is not a breeder with this hatch date and this hatch weight and female in brown. We predict, the Kate predicts that the treatment effect for that individual is -139. And then the next one is -161 and so forth. So we can see, like, we're actually making predictions conditional on having these features. This is what your treatment effect would be, not your outcome, but your treatment effect. Now, I never see the treatment effect for an individual chick. So what is it actually doing? It's you can think of the random forest, it's very closely related to a nearest neighbor sort of thing. So it's trying to find other chicks that are like that first chick in terms of their non-breeder and their hatch date and their grams, other ones that are close by and similar that got the other condition that were in the control, the opposite condition of this one. And then it sort of compares those. And that's where it's getting that conditional average treatment effect for the first chick. Let's see. So there's a lot of heterogeneity in these Kates. So there's a lot of variation. So I just plotted a histogram of them, and they go everywhere from like less than 180 grams, -180 grams, to more than -120 grams. So based on these modifiers, we're seeing a lot of differences in the predictions of the treatment effect for the bucket. They're all negative though. So the investigators are still not happy because their hypothesis is doesn't seem to be supported by this data. Maybe now is a good time to take a couple questions.
Yeah, it looks like we have quite a bit in the chat, starting with Jessica Vera asking, can we estimate p-values? I think that was on slide 32 back in the introduction of forest.
I don't think
Or
so.
like the tree, the bigger tree. Yeah, sorry.
This tree.
Yeah.
Nope.
Yes,
Still
this
no.
tree. Yeah,
The
31.
p-values?
Can we estimate p-values? Yeah.
So I haven't talked at all about uncertainty yet. So the random forests and the cart trees and the causal forests all are from a strong machine learning tradition where the focus is on prediction, not on uncertainty or inference, understanding how certain is our answer. So p-value is a traditional measure of uncertainty. And in causal forest, they won't give you a p-value, but they can compute confidence intervals for the predictions. Both their prediction for the individual treatment effects for each observation, for each vector of x's, this is the lowest and the highest that it might be. So that would be the equivalent of a p-value in the causal forest framework. I didn't get that far into the documentation to get that sorted out. I will show you the confidence interval for the overall average treatment effect, but you can also get confidence intervals for the individual level treatment effects. And that comes from, because you have all of these trees that are in the forest, you can kind of look across the predictions that you would get from all these different trees. And that gives you the range of likely values, or gives you some sense of the uncertainty about that prediction, what the range of reasonable values are for the prediction. But it is like different than you would get with a traditional p-value. Now you might be thinking, oh, well, I could run the causal forest, find the important variables, and then put them in a traditional analysis. That would be p-hacking, because the causal forest is designed to find the important variables. And so it would be a little bit like that p-value is no longer a reasonable estimate of the uncertainty. So yeah, I'm sorry, I don't have a more in-depth, I have like kind of a high fuzzy, this is how it's supposed to work, but I don't have the detailed code for you on that. The second question was, can we set the sample size of the trees in the regression forest? Yes, all of those parameters are tunable. So if you go, let's just go over here to the documentation. So bring up the help. So these are all the inputs. So sample fraction is what fraction you want pulled out to do the sample fraction. And then this honesty fraction. So this is, I didn't plan to get into this today, but you set the sample fraction and the honesty fraction. So first it takes off the honesty fraction and it uses the honesty fraction for computing the treatment effects. So, it uses that data to compute the carts, the individual level treatment effects. It doesn't use the data that was trained for the tree to do that. So it separates out into half the data is going to be for computing the treatment effects, and the other half of the data is for building the trees. And they do the build the trees first and then compute the treatment effects. And then they have to, when they're built, so they have this half of the data, if you use the defaults, that's left over for building the trees. And then when you build each individual tree, you sample half of that. And so it samples a quarter of the data to build each individual tree, but you can see those inputs can be changed. The honesty is very closely related to the idea of having like a holdout validation, but instead of for validation, we hold that out just for computing the treatment effects. So that if we use the same data to train the trees and to compute the treatment effects, we might overfit that data and then the treatment effects might not be accurate. So that's probably more than you needed to know about that. The next question is, how does this differ from principal components? I don't think of those two together. So principal components takes the data and tries to find the main forms of variation. So say you have this X vector, you're thinking, oh, I have this X vector and I could use principal components to find out what were the main dimensions of variation within that X vector. That's only within the X vector. The causal forest is for finding which of those X's relate to the treatment effect. So it's kind of a different purpose. Riffing on that, one thing that people sometimes do is they do principal components regression. So they take the principal components and make those predictors in a regression. That would be sort of somewhat related to this, but maybe not at all. I don't know. I wouldn't try to make too strong of a connection there. Does this mean the treatment effect 4 is the greatest? I'm not sure what slide Helen was on.
There was a slide showing all the predictions with the list like minus 139. Yeah, this one.
Oh, that set, it's not the biggest, but that is a high one. So if you're not a breeder and you start out pretty big and you are male and brown, then you're likely to have a big difference between the two treatments. But in this histogram, we can see they go all the way down to 180. So this was just the first couple of them. It goes off of the slide, but that's a good question. Okay, I understand that the parameter W hat in the causal forest is 0.5 for binary condition of the W indicator, but what if we have a continuous explanatory variable? So you can have a continuous W or continuous X, but not a continuous W, because the X's are used for the splitting, so it can decide continuously where to do the splits. But the W for the treatment effect, whatever your randomized thing is, you can only have discrete levels of that. The standard causal forest, you always have two. So there's always just a treatment and a control. I noticed when I was going through the documentation today that they have made a capability of having, I'm not sure where it was in here, but they have created a capability to have more than one treatment. And the other thing that's new that I saw when I was putting these slides together is that they can also take an outcome that's a survival outcome. So if you have a clinical trial with a survival outcome, you can analyze it with it's a different function. It's like causal forest survival, but you can still handle that kind of data. Hopefully that answers your question, Jessica. All right, good. So we looked at the heterogeneity in the Kates. The next thing I like to, this slide, sorry. I wanted to remind you guys that this is not the same thing as the random forest. So in the random forest, the random forest has predictions, and those predictions are for the grams day 25 variable. So there are numbers like from 1,000 to 1,100. The causal forest predictions are different. They're the treatment effect. So they're the difference between the bucket and the walk-on. And they're on a scale from about minus 120 to minus 180. So they're totally unrelated to each other. So the causal forest is doing something very different than the random forest. The random forest predicts those Kates. We could also plot the predicted Kates versus each of the modifiers. So we have one modifier that's color. So we can see here are the predictions for all the brown ones, and here's the predictions for all the white ones. Not too much action going on there. Here's the predictions for all the female ones, and here's the predictions for all the male ones. Also not a lot going on there. And here is the hatch date. So that's a continuous variable. So we can plot that against the prediction, and also not a lot of action going on there. So looks like yeah, not too much going on there. I'm gonna skip this one. So these plots that I just showed you, like plotting each predictor against the predictions, can kind of give you an intuitive sense for which predictors are important. Like if all the female ones have low predictions and all the male ones have high predictions, then we know that predictor is making a big difference in the estimate of the Kate. So that's somewhat unsatisfying. So the people who developed the package created this thing, it's called best linear projection. So you can use that function. And what it tries to do is find the linear model that is closest to the causal forest. So it looks more like a regular regression. Like that's what they were trying to do. They were taking something that isn't very much like a regression at all and trying to give you something that feels like a regression. So they're trying to like take the causal forest and kind of fit it as close as they can to a line. And these numbers here, like breeder, hatch date, grams, those are the effect of that variable on the conditional average treatment effects. So for instance, the breeder is minus 104 and female is plus 267. So those are in terms of the treatment effects. So the ones that are bigger, so brown, the color is the biggest treatment effect that we're seeing. And oh, Helen, a p-value. So this, because they're trying to squeeze it back into traditional statistics, they can give you the p-value for this best linear projection, and it looks like the brown is on the threshold of being significant at 0.05. So hopefully that answers your question, Helen. So that's one way to figure out which predictors are important. The other way is just to look at the plots and try to find the ones that are important. If you had a lot of them, you might look at this first to try to identify the ones that you want to look at plots for. All right, and we can also compute an average treatment effect from the causal forest. So it combines the Kates, this function average treatment effect combines the Kates to obtain an average treatment effect. There's some different options on how you actually do that. So it's not computing the difference in means, it's actually taking the causal forest and then trying to get an average treatment effect out of that. And there's the standard error on that, which you could also use to compute a p-value on that. So again, even using the fancy causal forest, sadly, the data just doesn't tell us that much about this effect. There's still a lot of uncertainty about this effect. That's why the title of the paper says a pilot study. The authors had done the basic difference in means when I got the data set, and they were like looking for me to turn their not significant p-values into significant p-values, but I couldn't. The data just doesn't do it. There was no magic that I could do that would make this data more informative. And that's because it's a tiny data set. So it's a nice example to use because it's small and you can kind of get a feel for the whole data set. But it's probably not the best thing to be using causal forests with. So causal forests really shine in situations where there's a ton of observations, where there's a ton of potential modifiers, and you're trying to sift through all of those to find the important ones. And I can see this being like, so this is a pretty new technology. I'm sure the FDA would not want you to run a causal forest on a clinical trial, say for vaccines. But if we get to the point where everyone feels comfortable with this method, then it could potentially help us, like, say you have a clinical trial on a cancer drug. You could take genomic data that is pre-treatment, the genetic characteristics of the patient who has the cancer, and you might have a lot of those, and you could put that into the causal forest on the clinical trial for the cancer drug to see who are the people that seem to benefit a lot from this cancer drug, and who are the people that don't seem to benefit very much from the cancer drug. And that would help you, think about, say, precision medicine. That's the promise of precision medicine, is that we would find really good estimates of who the medicine works for and who it doesn't work for, so that we can prescribe it appropriately. So that's the idea. All right, so just to summarize up, a causal forest builds on a machine learning model called a random forest to predict conditional average treatment effects. Hopefully you know what all those words mean now. And this allows us to quickly identify treatment modifiers in experiments so that we can find the people that are most affected by the treatment. And in marketing, this is really taking off because we often have very large experiments. Say we send people a catalog, but we have a control group that we didn't send the catalog, and we want to know, who does the catalog work for? And you can use causal forest to do this. And in marketing, we have a better name for it. We call it uplift modeling, because we want to know who are the people that get a big increase in their purchase amount if we send them a catalog. And causal forests are one way that marketers are doing these uplift models. And I'm actually going this summer to a workshop-based conference where a bunch of marketing professors are getting together specifically to talk about segmentation and targeting of customers based on this kind of data. And I'm sure causal forests will be on the agenda for that. All right, one last thing, I have some homework. It's totally optional, but if you were intrigued by this, it's kind of a sad story in that our analysis of the chicks experiment was limited by the small sample size, so we didn't identify any really strong treatment modifiers. And there's another thing I didn't show you, which is how to test the quality of your model using holdout validation, which is a technique from machine learning. So that's how people kind of confirm that their causal forest is well-tuned, by doing this holdout validation, which is kind of the standard analysis you would do in machine learning. So if you want to see that, the GRF tutorial, which I've linked there, it's here on the website under tutorials. It actually, if you skim past the math, you kind of know most of what the math has to say, because I've already said it today, and start to go into the applications. There are data sets that you can download and run this code, and it'll give you examples of what this looks like with a very large data set. And I actually stuck it in the GitHub repo, a version of the code, so school program evaluation. And let's see, just see if I can run this real fast. It's going to be slow. It takes a few seconds to run the causal forest. This is a big data set. It's on a treatment that students got in school to help them have better jobs in the future. And it has 17,299 observations. Let's see the plot. So the biggest predictor in this data set is a variable called financial autonomy index, which is something about the students' financial autonomy before they got the treatment. And these are the predictions plotted on the y-axis. So you can see there's like definitely like that matters until you get to about 40, and then it doesn't matter. If they're above 40, kind of the predictions flatten out. And this prediction here is the effect of that educational intervention on some kind of economic outcome in the future. Sorry, I don't know all the details, but I wanted you to see a picture of what it might look like. And that data set has like 20 predictors, and it very quickly finds the top predictors. So you might want to look at that tutorial if you want to know more. But hopefully I've kind of opened the door so you know why you might want to do this. You should try it on your own experiments. The last little tidbit. Suppose you have something that wasn't an experiment, but you have a treatment and control that were observational. They weren't randomly assigned, but you have the treatment and the control. If you have all potential confounders, then the estimated ATE will be causal without the randomization. Now that if is a big if, but people are using this in economics in situations where they can't randomize to try to estimate the effect of, all kinds of things that people might have, experiences that they might have on on the outcomes, the late downstream financial outcomes that they have. All right, so that's it. Thank you guys so much for having me. Apologies if I really scrambled to get this together, so it's not up to my normal standard of no typos and everything being clear and well explained, but hopefully you got the idea and enjoyed learning about this, and it was great. Thank you for all the questions.
Thank you so much, Ellie. That was fantastic. No need to say sorry. It sounded like everyone enjoyed it. We do have a couple questions in the chat. If you want to stop sharing your screen, I can go ahead and post the winners and instructions while you go through those questions if there's time.
Okay.
Yeah. So the winners of the talk, really briefly, sorry, will be getting this book by Julius Silge. And we have ebooks and hard copies, so I'll go ahead and start the slideshow. So today's raffle winners, and I made sure that they were all in the event today. It's Kevin, Liz, and Helen. So congratulations, you guys. Please email us with your email address or physical address, and we'll go ahead and email you the prize. And that's all for us at Our Ladies, if you want to briefly touch on those questions.
Great. So John asked if this is for categorical versus regression. So this is for outcomes that are continuous. So I think more like what you're calling regression. So your outcome should be something that's fairly continuous. If you had like a 7-point Likert scale, it would probably still work. But if you had like an outcome that was binary, like click or not click, it still might work. It might work. I don't really know the answer to that, but it's intended for a continuous variable. Helen asked, can it be used on survival outcomes? And I guess I already covered that. So yes, it's been extended for survival outcomes. I haven't read the papers for survival outcomes, but it should be a pretty straightforward extension. I don't know anyone who's had experience using it for survival outcomes, but hopefully you can report back on what you find, especially if Alice or Helen tries that out. Sandra is asking, can you touch on how different industries or companies use those terms, statistical analysis or machine learning? I'm doing my MS in data science, and one internship used machine learning for black box models and not statistical analysis. I think that's a big distinction. I mean, it's really a social construct. So statistics was developed by statisticians and econometricians and biostatisticians that were all doing kind of this traditional form of modeling that very much centered on that linear model. There were relaxations of that, but that was kind of like the workaday tool of analysis. And it also centered on the p-values that Helen brought up, this as a measure of how certain are we about things. And then the machine learning algorithms were kind of invented on the side by computer scientists who didn't know much about what statisticians had already done. And they built these they had better computers, and they built much better, more flexible algorithms. And they really focused on prediction. They didn't think about like, am I sure about what the average treatment effect is? They were thinking about, which is probably what Alice works on in her job. Like she really wants to know what that average treatment effect is and how sure, like how low could it be and how high could it be is really important. Whereas the machine learning people focused on prediction problems, like, is it going to rain today? And they just were worried about whether or not they got the predictions right or not. And causal force is kind of an interesting case because it sort of fused the two ideas together. So you see there's some aspects of it that are very traditional statistics. It was invented by econometricians, economists that specialize in statistics. But they had some exposure to these machine learning algorithms and kind of put the two together to do something super useful. So this is sort of betwixt in between those two worlds. I don't know, other people may have thoughts on what is machine learning versus statistical analysis. I think it is a sort of a moving target.
I posted a recommendation. Sorry, just to jump in. Everyone should read The Chief Cultures of Statistics by Brayman, because it talks a lot about that, about how computer scientists versus statisticians. And it's a very old paper, but it's very relevant. I'll just put a recommendation.
Okay, yeah, no, I totally agree with you on that, Alice. The last question was, can we tune the hyperparameters? So that's a very machine learning kind of question. So what Chun is asking is, there's some rules for how those trees get built, and those are called the hyperparameters. So they're the rules like how small can a node get, and how good does the split have to be before I'll actually add it to the tree, and so forth. So yes, they are. The answer to that is yes, you can tune the hyperparameters, and the package includes auto tuning. So the ones that I ran today were auto tuned. But when you auto tune, you have another, so you have your honesty sample, you have your holdout sample for the tuning, and you have the sample for building the trees. And so it starts to cut the data very, very thin. But yeah, you can definitely do that tuning built in. All right, I think that's all the questions. Thanks for sharing that, Alice. All right, how do we end this thing?
I was saying, we just say thank you.
Yeah. Thank you so much, Ellie.
Oh, you're welcome. It was fun. Thanks for all the questions.
Yes, it was great. Thank you everyone for attending. Thank you enough. I can't thank you enough, Ellie, for a great talk.